Hello students, in this video I'm going to be going over the practice exam for the second instructor exam. This is a review of all the different topics that are on that exam, including probability, talking about regression, and also looking at tree diagrams. These are all types of questions that you might see on the second instructor exam. I have the answer key here, I scanned it in, and I'm going to be going over each of the answers individually. Here we go. For 1A, it asks us to roll 2 dice. So what I did was I wrote down the sample space here. This is all the different outcomes from the event rolling 2 dice. Notice that R1, that's the first roll, is going to be down here on the vertical axis, and the horizontal axis here is R2, the second roll. So for example, if I'm looking at this row, which is 2, and this column, which is 4, that represents 2, 4, the first roll being 2 and the second roll being 4. When you roll 2 dice, what's the probability that the sum is 7? There's a lot of different ways to get this, but the easiest way to do this is to list out the sample space and actually count the number of outcomes that give you a sum of 7. And I outlined them in green here. 6 and 1, 5 and 2, 4 and 3, etc. All of these give us 7. There's 1, 2, 3, 4, 5, 6 outcomes. And in total, when I roll 2 dice, I am getting 36 different possible outcomes. So 6 divided by 36 is equal to 1 out of 6. For the second one, you're drawing 4 cards from a standard deck, which is 52 cards. Without replacement, that's important. You're not putting them back. If I was asking you whether this was independent or dependent, these are dependent events because when you do it without replacement, you don't put the card back, which means it changes the probability. What's the probability that they're not 4 of a kind? Well, if we're looking for the probability of not 4 of a kind, we have to do 1 minus the probability that there is 4 of a kind. So 1 minus this probability. I'm looking for 4 of a kind. So let's say, for example, I'm looking for kings. There's 4 kings in the deck and 52 cards total. So 4 out of 52 is the probability of picking the first king. After that, there's 3 more kings left because remember, we don't put them back. And there's 51 cards because remember, we don't put them back. So 4 kings out of 52, and then on the second draw, it's 3 kings left out of 51 cards. On the third draw, there's 2 kings left out of 50 cards, and then 1 king left out of 49. If you multiply all these together in your calculator, you get a scientific notation number. Instead of writing down that scientific notation number, I'm just going to use math enter to turn into a fraction. So 1 minus 1 divided by 270,725. This is an acceptable answer. You could also use the scientific notation, but I think that using fractions is probably more comfortable for students. For question number 2, actually, before I talk about question number 2, let's cover this up because this is the probability of them being 4 of a kind, so they're not actually equal to each other. This is the answer we're looking for, which is 270,724 divided by 270,725. This is the answer we're looking for. I think the decimal equivalent is 0.999, etc., so it's probably easier to write it as a fraction anyway. For number 2, the probability that Sam is accepted and obtains a scholarship, that's the probability of A and S. I'm calling A accepted and S scholarship. That's equal to 0.35. The probability that she is accepted by the college, just the probability of accepted, is 0.65. So that's the probability of A there. It's asking here what the probability is that she obtains the scholarship given that she's accepted by the college. So the probability of scholarship given, that's this vertical line here, that she's accepted. There's a probability formula for this. The probability of any event given another event is equal to the probability of both of those events happening at the same time. S and A, divided by the probability of that given event, which is A in this case. We have both of these. A and S is the same as S and A because if 2 events happen at the same time, it doesn't really matter which one is written first. So that's 0.35, and I know the probability of A is 0.65. This was just a plug-in question. You could have left it like this, which is a rounded decimal, or you could have turned it into a fraction. For number 3, it deals with binomial probability. And remember, there are 4 different things that we need in order for a situation to have binomial probability. We need fixed trials, a certain number of trials. We don't, keep going until we succeed. We're saying, we're only going to draw 10 cards, or we're only going to take 6 penalty shots. The probability of success has to be constant. Every single time she takes a shot, the probability is 75% that she succeeds. Independent trials, in other words, if she makes a shot the first time, it's totally independent on whether she makes the shot the second time. And we're assuming that these are independent trials. That's what it says here. And we also need 2 mutually exclusive outcomes. Well, if you've ever seen hockey, you should know that the 2 different outcomes are either you make a goal or you don't. In this case, we're using the probability formula for binomial probability. Let me slide this over a little bit. It's this formula, which you should remember from the slideshow and you should remember from the video. All you have to do is fill in the information from that. 6 is the number of trials. 0 is the number of successes. This is the probability of success. 0 is the number of successes. This is the number of failures. And unfortunately, we're talking about making none of her penalty shots. That's 6 here. So that means 0.000244, etc. There are a number of different ways to represent this. This is scientific notation. This is decimal form. This is fraction form. Doesn't matter. Use either. Letter B, we could have done a lot of things added together, like the probability of 1 plus the probability of 2 plus the probability of 3. That would be arduous. Another way to do it is finding out the probability of none, which we already did, and subtracting that from 1. Because think about it. The probability that she makes at least 1 is the opposite of the probability that she doesn't make any of them. It's the opposite of that probability. We refer to this as the complement rule. In other words, the probability of one event happening is equal to 1 minus the probability of the opposite happening. That's complement probability. For letter C, over the course of a career, she takes 250 shots. We're calculating the expected number of shots, otherwise known as the mean number of shots for the distribution, and the mean of a binomial distribution is just n times p. It's a very simple formula that you will be given on the test. Just multiply them together, no big deal. Letter D is another formula question. The formula for binomial probability standard deviation is just this. It's the square root of n times p times 1 minus p, the number of trials, the number of success, the probability of success, and the probability of failure, respectively. Not too bad. For number 3, we're given a situation in which we have to make a scatter plot. In this scatter plot, it talks about the average monthly temperature in Queens and the average monthly sun hours in Queens. This is actually real data from the NOAA. I looked it up myself. Anyway, for example, in March, the average temperature is 42 degrees, which seems pretty cold, but as you can see, it's getting warmer and warmer and warmer, and then it goes back down. Anyway, here's the scatter plot, and you should know that the first value here is the x value, the x variable, also known as the explanatory variable. You should remember that x is the explanatory, and then response variable is y. So we have the scatter plot here, and notice that it has that pattern that seems like it's increasing pretty steadily here. And one other thing that you should notice is that on the x and y axes, we didn't start at 0. We actually jumped a few before we got to the first line that we labeled. So we have to use this, which is called a break. It's representing the fact that we didn't jump from 30 to 0 here. We actually broke, and we actually skipped a bunch of numbers before we got to the first number. Notice also that when you're making a scatter plot, you must have the labels on both axes. For letter B, we talked about least squares regression lines or line of best fit in the notes. All you have to do is go to your calculator. You're going to press stat edit to put in the information. You put in this information. L1 is all of these numbers. That's the x values. And L2 is all of these numbers. That's the y values. So when you put them in, then you press stat and then calc, and then go to linreg, linear regression, and you're able to get the values of A and B. A is 3.0623, B is 56.2608. Long story short, we put those together into this equation using AX plus B. For letter C, it talks about approximating the correlation coefficient. If I look at this, I can draw a line of best fit that kind of goes through here. It looks like a fairly strong relationship. The line would probably be fairly close to most of these points. So I'm going to say that this is a fairly strong relationship. My guess was that it's about 0.75. However, when I did it in the calculator, if you remember from the notes, you had to go to the catalog and turn on diagnostics on. You found the correlation coefficient was 0.9058, a little bit stronger than we thought, but still a moderately strong relationship. As long as you were positive, because remember, the positive number represents the fact that the numbers are increasing, and as long as the number was close to 1, you would be good to go with that approximation. And for letter D, using the line of best fit, what we're going to be doing is making an estimate. So we know that the average temperature in March was 49 degrees Fahrenheit. So we're going to take this value, which is the x value, and substitute in here for x. And then solve it. We get 204.5495. It's about 204.5 hours of sunlight. I just wanted to go over those steps for the calculator again very briefly. So I have my calculator here. Let me slide it out of the way a little bit so we can see all the data. And remember, what I asked you to do is go to stat and then edit. So what we're going to be doing is putting the x values here for L1 and the y values here for Y2. All right, as you can see, I put all those numbers in here, and you can see that L1 is all the X values, and L2 is all the Y values. We stop at the 12th value for both of them, and they both line up at 39,155. Great. Now what I want you to do is go to Stat, and then go to Calc, and then go down to LinReg. That's the one I was talking about before, linear regression. When you press the enter, you get 3.02625, etc., and then 56.2608. That was the answer that we got here. Now, if I'm trying to find the correlation coefficient, you need to go to the catalog, which is here. I press second catalog, and I'm going to scroll down or use the D button, which is here. You can see the letter D. I'm going to go to where it says diagnostic on, press enter, and then press enter one more time until it says done. Then I'm going to follow the same procedure, stat, calc, linreg, and I'm going to get the same A value and B value, but I'm also going to get R squared and R. R is the one we're looking for, not 0.9058. That is going to be the correlation coefficient. All right, moving on to the next problem. On question number 4, it gives us the two probabilities. And look, this is another probability formula question. The probability of A given B is equal to the probability of A and B divided by the probability of B. So it's very straightforward to do. For the second one, it asks whether we can find this probability, and we can't because we don't know the probability of A. The difference between these two things is that B is the given here, but A is the given here. And remember, we're dividing the fraction by the probability of the given event. So we put B on the bottom here, and we would normally supposed to put A on the bottom here, but I don't know it. So unfortunately, we cannot find this probability yet. For letter C, it asks whether the two events are mutually exclusive, and the easiest way to tell whether two events are mutually exclusive is to look at the probability of A and B. Remember that mutually exclusive means they can't happen at the same time. So if there is a probability of A and B, in other words, those two events happening at the same time, then they can't be mutually exclusive. In this case, we know that the probability of A and B is 0.3. It's not 0, so these are not mutually exclusive. If these two events were ME, we call that mutually exclusive, then A and B would be equal to 0, but it's not. For letter D, it asks whether the two events are independent. There's another rule that tells us whether the probability of two events are independent, and that's if the probability of A and B is equal to the probability of A times the probability of B. Independent events should have a product of their probabilities that's equal to the probability of both events happening. But that's not the case here because the probability of A is 0.15, probability of B is 0.5. That's I think this should say 0.075. Let me check that. Oh yeah, it is 0.075. Let me go ahead and fix it. Oh, I don't have to fix it. It's already correct. How about that? All right, for question number 5, it asks us to figure out a probability distribution for this 3-coin flipping game. I wrote out the sample space the same way I did for the dice before, and then I wrote down the number of heads for each of these different outcomes, and then I calculated the probabilities for each. For example, the probability of 0 heads is 1 out of 8 because only one of these outcomes has 0 heads in it. So then I also put down X, the random variable, being the amount of money that you win for the payouts, -10 for lose $10, 1 for win $1, etc. And then the question was, would you play this game? Well, the answer is yes, because if you calculate the expected value, the value of an average payout, it's 0.5, which means that on average, if you play this game many, many times, the average payout of one game will be 50 cents. You obviously can't win 50 cents in any of these individual outcomes, but in over a long period of time, on average, you're going to win 50 cents per game. So if you play this game 100 times, you're going to win $50. Very good. As long as it's a positive number, you say, yes, I do want to play the game. Last but not least, I wanted you to take a look at this tree diagram. Let me try to shrink it so you can see the whole thing at once. All right, now it's shrunk down a little. You can see that the tree diagram has a number of splits equal to the number of individual events that happen. This first split represents the first draw of a marble. The second split represents the second draw of a marble. And you can see all the probabilities are calculated here. Not too bad. Using the tree diagram to calculate the probability that you draw 2 blue marbles given that you draw 1, well, we use the same formula as before, the probability of 2 and 1 divided by the probability of 1. Looking at the different events here, this is the only probability of drawing 2, so that is the top number. The probability of drawing 1 blue marble is this one, plus this one, plus this one. And there's our answer. All right. This was a video that reviewed the second practice exam. Good luck studying.